Okay, everyone. Here we go. So, picking up where we left off, I want to cover some more basic probability results that we can derive from the Kolmogorov axioms of a probability function. These are going to be super useful for us from now on. So, let's begin with a probability space and a couple of sets in the sigma algebra. And let's work on number one first. To show that probability of B intersection A complement can be given by this, we can start by writing the set B as the union of B intersect A and B intersect A complement. Now, these two are disjoint, so we can write probability of B as the sum of those two probabilities. B intersect A plus probability B intersect A complement. Then we can rearrange this and get B intersect A complement is equal to probability of B minus probability of A intersect B. So if we draw a picture of that one, it makes a lot of sense. This is like B intersect A complement is like this. We could represent the probability by shading this area. And so it's like we take all of B and we take away this part, which belongs to A. Okay, we went over kind of quickly this idea of having like the probability of the union of disjoint sets as the sum of the probabilities. And so I want to go back and discuss that again. Or discuss it really for the first time. I skipped it, I think, because I was getting frustrated at the internet connection. One of our Kolmogorov axioms is this axiom of countable additivity. But we can show that countable additivity implies finite additivity. Let's go ahead and show that. So countable additivity is finite additivity is when we just have n of these, and we want to say that the probability of the union of disjoint sets is equal to the sum of their probabilities. So I can prove it by saying for any a1 through an which are disjoint, this all means they're pairwise disjoint, I can set an plus 1 equal to the empty set, an plus 2 equal to the empty set, and so on. And then I can write union of all those an's out to infinity is going to be equal to the finite union, because after I get to n plus 1, they're all the empty set. So now I can write probability of this by countable additivity is equal to this sum of, probabilities, sum of probabilities, and this sum of probabilities is equal to just the sum of these probabilities of the first n events, because probability of the empty set is 0. That's how we can have equality there. And maybe let's move this down. Because these are equal, I can say probability of this finite union is equal to the probability of this countable union, which is equal to this countable sum, which is equal to this finite sum. So if I have just n equal to 2 and my events are A and B, then I can say probability A union B, and this is where A and B are disjoint. So we're talking about A and B not overlapping. Then the probability of A union B is just probability of A plus probability of B. We use this all the time. All the time, all the time. Okay, so going back down to what we're now showing. We wanted to show this one, and we started by writing B as this union of two disjoint events, two disjoint sets. And so then I can write probability of B as the sum of these two probabilities. So here I'm really using finite additivity to get that equal sign. Okay, good. Now let's move on to the second one. So how can we show this? Okay, so let's start by rewriting A union B in a different way. Let's write it as A union B intersect not A. I think we proved this much earlier in the slides. I don't want to scroll up and down. If you have doubts, you can draw a picture. I think we did a rigorous proof. So A union B is all of this stuff, but we can write it as all of A union with the part of B which is not in A. And so if we take the union of all that stuff, we get the whole thing. Okay, and these are disjoint. So we get a lot out of writing something as the union of two disjoint sets. Okay, so now I can write this as probability of, well, sorry, I'm not writing it as a probability yet. So probability of A union B is then probability of A plus probability of B intersect A complement. And from up here, from our earlier work, I can pull that down and say that this thing is probability of B minus probability of A intersect B. Okay, so that's the whole thing where when we teach our intro to statistics course, we say, when we use this formula, we draw the Venn diagram and we say, if you take probability of A and then probability of B, then you're counting this middle part twice, and so you've got to take it away. Take it away by subtracting the intersection. Okay, but pictures aren't quite good enough for us now that we're in graduate school. Okay, so number 3. This says if A is contained in B, then the probability of A cannot be any bigger than the probability of B. Maybe I'll not use pink. So if A is in B, probability of A cannot be bigger than probability of B. How do we show this? So I've got A contained in B. Here's what we can say. If A is contained in B, it means A union B is simply B. You could show that, but like if this is A and this is B, then the union is just B. You can keep this picture in mind. Okay, I'm trying to move it to the side. Okay, so that means if I go back to this expression that I got for probability of A union B and put like A union B is really just, here, let me put it over here. Probability of B is equal to the probability of A union B. Since under this, if A fits inside of B, then these are the same. So now I'm going to pull this down and put probability of A plus probability of B intersect A complement. And now I know since this is a probability, it has to be non-negative. And so if I get to the probability of B by taking probability of A plus some non-negative thing, I must have the probability of A is not bigger than probability of B. Okay. Good. So we are going to use that fact all the time. Okay. Okay, a couple more important rules of probability that we use all the time. The first one we often call it the law. Well, it's written right here. We call it the law of total probability. That's the first one. Let me choose a less nasty color. Law of total probability. And the basic idea behind the law of total probability is that we have some partition of the sample space. Partition, again, means that the union of all these sets gives us the whole sample space, but they're pairwise disjoint. So Ci intersect Cj is empty for all I not equal to j. Okay, then we imagine there's some set A, and we'd like to compute the probability of A. And so if we represent the probability of A by shading this area, we see that it's composed of a few different pieces. There's this part, there's this part, there's this part, and there's this part, for example. So the idea is to use the partition to break A into these disjoint pieces. And so we can write A as the union of A intersect Ci. Anytime we have a partition, we can always write A as this union. Okay, and since these are pairwise disjoint, I can say probability of A is the probability of this union, A intersects Ci. I can write this as the sum of probabilities A Ci because of countable additivity. So that takes care of the first one. That's called the law of total probability. The second one, which we call the union bound, sometimes people call it Boole's inequality. I need to remind myself who Boole is. Can't tell you any interesting stories at the moment. The union bound is very important. It's used all the time. It says the probability of the union of any events is bounded above by the sum of the probabilities of those events. We can understand it intuitively by drawing a picture. Let's say I've got some sets like this, I don't know, A1, A2, A3. The union I can represent, let's say the probability of the union I can represent as this shaded area. But if I were to to add the probabilities of the individual events, I would take this area plus this area plus this area, and they wound up kind of double or triple counting all of this stuff in the middle. And so it's easy to see that the probability of the union is going to be less than or equal to the sum of the individual probabilities. How do we prove it apart from, how do we actually prove it instead of just drawing a picture? Our strategy is going to be to try to write this union as a union of pairwise disjoint sets. So pairwise disjoint sets. So let's define some useful sets. Let's define B1 to be A1, B2 to be A2, but the part which is not in A1. Then B3 is going to be A3, but the part which is not in A1 or A2. And let's keep right on going and define beta n as the part which is, is AN, but only the part which is not in the union of A1 through AN minus 1. What does this look like? If I copy and paste this, the BNs are kind of like this. B1 is just equal to A1, but B2 is only this new part when I'm taking the union of the A's. So B2 is only this red part, and then B3 is only this part. So it's just the new part, B3. Now we have that the union of all these A's can be expressed as the union of all these B's. So we still pick up everything by taking the union of the B's, and moreover, the B's are pairwise disjoint. Okay, so none of these B's overlap with other ones. So I can write probability equals probability then of this union of disjoints, pairwise disjoint sets. By countable additivity, I can write this as sum. And what were we trying to show in the end? Remember, I was trying to show that that this is bounded above by the sum of the individual probabilities. So in a final step to show this, I just need to observe that I can write A1 contained in B1. I can write A2 contained in B2. Remember, this equality means I have containment in both directions, so I'm good there. Since B2 is A2, take away some part of it, I have A2 contained in B2, I have A3 in B3, and for all of these I have AN is always contained in Bn, which means probability of Bn is less than or equal to, probability of, I'm doing it all backwards. Which one is bigger? B2 is contained in A2. because to get B2, I take A2 and I take away some part of it. So B2 is in A2. B3 is contained in A3, and all the way down, Bn is contained in An. I had it backwards. This means that probability of Bn is always bounded above by the probability of An, which gives us an inequality here, and that's the one that we wanted. So we're done showing the union bound. Another useful probability rule is called the inclusion-exclusion principle, or you might call it the inclusion-exclusion formula. And it looks kind of confusing. It can look a bit ugly, but it can be useful. You're using it on some of your homework problems. So given a probability space and some events in the sigma algebra, if I want to compute the union of A1 through AN, I'm not assuming they're disjoint. This is for any sets. They can overlap in any kind of way. I have this kind of crazy formula for it that always holds. And to make sense of this formula, I want us to just write it out when n is small. So let's look at this. When n equals 2, I have only two events. I have A1 and A2. And so probability of this union is just A1 union A2. And I want to use this formula now to write it down. I know what I'm going to get already because we worked out that this is probability of A1 plus probability of A2 minus the probability of intersection. But let's see how this inclusion-exclusion principle gives us the same thing. So I need to put S1 minus S2 here, where S1, looking at this, is like, let's just write it out. Okay, I have a sum. My n is 2, so I'm going to put I1 up to 2, probability AI1. Okay, that's how you work this out when n equals 1. So this is going to be just probability of A1 plus probability of A2. Now S2 looks like a sum, and now I've got two of these little indices, I1, I2, up to n right here. My n is 2, so probability AI1 intersect AI2. Now, there's only one possibility for I1 and I2. They have to be just 1 and 2. Okay, that's the only thing they can be. So what I have in the end is probability of A1 union A2 equals S1, well, S1 minus S2. S1 is this, so it's probability A1 plus probability A2 minus S2, which is this. So I get probability A1 intersect A2, which we knew we would get. Let's do n equals 3. So I have 3 events now. A1 union A2 union A3. This is S1 minus S2 plus S3. Where now S1, these really depend on n. Maybe I should add an extra indicator or notation there. Okay, so S1 is going to be a sum of these, but where there's only one one probability in here. So this is going to be sum I1. My n is 3, AI1. So that's probability A1 plus probability A2 plus probability A3. As 2, I now have two indices in here. I1, I2. So we've got some possibilities now. I could have A1 intersect A2. I could have A1 intersect A3, and then A2 intersect A3. Now as 3, I've got I1, I2, I3, and now I've got an intersection of these three events. Now there's only one way I can have three unequal integers between 1 and 3. So this is like this. So in the end I have that this union is equal to the sum of all the probabilities minus all of these intersections, every possible intersection we can think of between two events, A1, A3, plus this intersection of all three of them. Like that. So that's how you use this inclusion-exclusion formula. Okay. So how would you prove such a thing? Let's think about it now. The easiest way to understand the proof is to assume the sample space is discrete. So you have just these outcomes with these associated probabilities P1, P2, and so on. And what you can imagine is you've got this union over here on the left-hand side, and then you've got this stuff plus n minus 1 over on the right-hand side. And if you imagine computing this probability, you're going to be summing up these little p's associated with the outcomes. So let's consider the contribution of a single outcome, let's say omega j, to each side, to each side. That is, got the right-hand side, or right-hand side and left-hand side. Let's consider the contribution of a single outcome. So suppose this single outcome is in some number m of these. So we know it could be in more than one of those sets because those sets could overlap. So let's say it's in exactly m, where this m, like it could be 0 all the way on up to m, or all the way on up to n. Okay, so on this side over here, I'm only going to get like pj coming into this probability. So I'll put pj times 1. On this side, if I count up what I'm going to get, if wj is in exactly m, of these. Then from S1, remember S1 is going to be like it's the sum of these individual probabilities. So if my outcome isn't exactly m of those, I'm going to get pj times m coming from this one. S2 is this we've got this intersection between two of these. Now, if my point isn't exactly, if my outcome isn't exactly m of these, then I can think of like how many times am I going to add this probability pj up when I take this sum, and it's going to be m choose 2 times. Well, and I'm subtracting s2. Okay, so we'll get into some counting rules later on, but this is like I can choose. There are this many ways to choose 2 of the m. Now S3, this is I1, I2, I3, and here's where I've got I1, I2, I3. And so this is going to be, when I consider the contribution of this outcome to this probability, if it isn't exactly m of the events, then I'm going to be adding up its probability pj, m choose 3 times when I take this sum. And so if I kind of, at this point, put dot, 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 and then I've got this end of the formula, I'm going to come out to like Sm, where I would be adding up m choose m, and this would be m minus 1 times that probability pj associated with that outcome. Okay, and so this was like the contribution to the left-hand side, and all of this was the contribution to the right-hand side. We need to show that they're equal. So I have pj everywhere, and on this side I just have 1. So if I bring that 1 over to the other side, it looks like the whole equation looks like minus 1 plus m minus m choose 2 plus m choose 3 minus dot 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 plus minus 1 to the m minus 1 m choose m. I guess let me move this down. So, so if that equation up there is true, it's equivalent to this equation down here. Let me write this as minus m choose 0, and let me, so let me put minus m choose 0, and let me write this as m choose 1. So what I have here, so we're asking again if this is true. So is this true? Let's look at this side. If I take a minus 1 out, I can write this as sum of m choose I going from 0 to m, and then I've got a minus 1 raised to the I, and then I can think of there's a 1 here raised to the m minus I. All of this is equal to 1 minus 1 raised to the power m by the binomial theorem. So if I want to write a plus b to the power n. This is n choose I, a to the I, b, n minus I equals 0 up to n, the binomial theorem. So this really does equal 0. Yes. Yes, really true. So that means that's our justification for the inclusion-exclusion principle. The left-hand side is equal to the right-hand side. You can see this by counting the contribution of a single outcome to each side and noting that it's the same. Bonferroni inequalities. These are kind of related to the inclusion-exclusion principle. I'm not going to go through a proof of them, but I just want to show you what they look like for a couple of cases. So basically, the Bonferroni inequalities tell us when we set up the inclusion-exclusion principle, let's say we just stop here, then we get this inequality. But if we stop here, then we get this inequality. And if we stop here, then we get this inequality, and so on. So we can compute this exactly, this left-hand side, we can compute it exactly by including all these terms. But if we want a lower or upper bound, then we can just stop after a certain number of terms and get a lower or upper bound. And that's what this is telling us. So here it's like I keep m of those terms. So it's just like keep m terms in the inclusion-exclusion formula. And then you get inequalities instead of an equality. Okay, so let's say I just keep m equals 1 term. If I just keep n equals 1 term, then m is odd. And this tells me that I just have, let's see, minus 1 times 1 S1, which is just S1. Remember, S1 is just the sum of the probabilities. And this is what we already know as the union bound, that inequality. This is an inequality. That's the inequality we already know as the union bound. M2, if I keep the first 2 terms, I get an inequality going in the other direction. So I first get this, then I get this. So I get sum of these guys, sum of the probabilities, minus now sum, n, the sum of all intersections between pairs, I1, I2. And that gives me an inequality going in the other direction. Okay, so you can keep as many terms as you want. If you keep all n terms, you exactly compute the left-hand side. If you keep only some of them, then you get inequalities. So sometimes it might be a burden to compute all of these. It might be too hard, but maybe you just need to compute the first 3 and the first 2, and this gives you a lower and an upper bound and a reasonable approximation to the union inequality. Okay, or to the union probability. Okay, I also want to talk about statisticians often when we say Bonferroni's inequality, we're referring to not necessarily to these Bonferroni inequalities. So here's how statisticians often use one of these inequalities. We reformulate it into this other, so that it looks like this. I'll show you how we do that. We often use this inequality. It says for any events A1 through AN, the intersection probability is at least 1 minus the sum of the probabilities of the complements. I'll show you why that's useful in a moment. But first of all, let's figure out why it follows from the union bound. Let's do the work up here. So let's say I have A1 complement through AN complement. These are in my sigma algebra. I know the probability of the union of these complements is less than the sum of the probabilities of the complements. This is just the union bound. Now, this union of complements, if I take the complement of it, it gives me the intersection of these by De Morgan's laws. So I can write this probability is equal to 1 minus probability of the intersection of the AIs. Okay. This probability is 1 minus the probability of its complement. That's where I'm getting this. And so rearranging everything, we see that we're going to get the result, because this thing goes, okay, let me just, I'm running out of space there, but coming down here, we have that this is like that. So coming here next, and that gives probability intersect AIs. If I move it over to the other side, then I have this. Okay, so that proves the result. When would we use this? We're not going to talk in this class about constructing confidence intervals, but this is something I think we're all familiar with. There's a pretty commonly used adjustment to confidence intervals called the Bonferroni adjustment, and it's based on this inequality, and it's when you, let's say you want to estimate a bunch of different things, like let's say you want to estimate these n different parameters, and for each parameter you construct a confidence interval with some level of confidence, 1 minus alpha. So maybe you could set alpha equal to 0.05 and construct a 95% confidence interval for each of these n parameters. You might be interested in the event that all your confidence intervals contain their target parameters simultaneously. So if AI is the event that the ith confidence interval contains its target, then what we can do is think about this event of the intersection of all those AIs. This means all CIs capture target. And this happens with probability at least 1 minus the sum of the complements. So let's say I make, let's say the probability of each AI is alpha, sorry, is 1 minus, let's say it's 1 minus alpha. If the probability of each confidence interval covering its target is 1 minus alpha, then this is like 1 minus n times alpha. And so if you build like a bunch of 95% confidence intervals where alpha is 0.05, then like if you build n of those, the probability that they all capture their targets is only guaranteed to be as great as 1 minus n times alpha. So what people do sometimes is they adjust their confidence intervals so that they use some alpha star, and then the simultaneous coverage probability, sometimes called the family-wise coverage probability, is guaranteed to be at least this great. And what they can do is set this alpha I, where alpha star is equal to alpha divided by n. And so if you do that, you get, you're guaranteed at least 1 minus alpha, with probability at least 1 minus alpha, all of your confidence intervals will simultaneously cover. So, so this is called a Bonferroni adjustment. Bonferroni adjustment to confidence intervals. So if you build confidence intervals with a smaller alpha, they get wider, but you ensure that if you're building a bunch of confidence intervals and you want them all to cover simultaneously, you need to make this adjustment. Okay, so that uses this Bonferroni inequality. So we've made it through like the basics of probability theory. We're going to have occasion to talk sometimes about sequences of sets and how the probability function can be considered a continuous function. First, we need to talk about sequences of sets. All right, so you guys know about limits of sequences of real numbers. So if you have a sequence of real numbers, you know something about how to take the limit of this, and we're going to discuss now what it means to have a sequence of sets which have a limit. So let's say we've got a sequence of sets. We're going to say the limit exists and is equal to A, so we'll represent the limit with A, if something called the lim sup and the lim inf of the sequence both exist and are both equal to the same thing. And how we define lim sup and lim inf for sets is in this way, which looks a little bit scary. Lim sup, we have intersection of unions, and lim inf, we have union of intersections. I want to come right down here and try to make some sense of these definitions of lim sup and lim inf, or at least give some interpretations of them. This one, if we say, if there's an outcome contained in this set, which is the lim sup, then we find it means that this outcome, well, we say that it occurs infinitely often in the sequence. And if an outcome is in this lim inf set, we say that it occurs eventually. And so I want to kind of go through what we mean by that. Okay, so the lim sup of a sequence of sets AN is just writing down the definition. You start with intersection and then you do union. Let's try to make sense of this. So this one goes from n all the way up to infinity. This one begins at n. This should be a k. Begins at n and goes to infinity. So the way we can write this is it's like outcomes such that for all n greater than 1, this is coming from the intersection, there exists k greater than or equal to n such that the outcome is in AK. So this means no matter what n you choose, I can always find beyond that n some set which contains omega. So it's all of those omegas. And so we say that this is the set of omega which occurs infinitely often. That's our phrase for this whole thing. So basically, omega is in an infinite number of these AKs. Because for every n, I can find a set AK beyond n, which contains omega. So so we say this is omega, which occurs IO, which means infinitely often. This lim inf of AN is union intersection k equals 1 to infinity AK. This one is outcomes such that there exists n greater than 1. So for some n greater than 1, such that this is n, such that omega is in AK for all k greater than or equal to n. Okay, and this for all is pointing back to this intersection. So maybe I'll put here for all, that's the intersection, and there exists points to the union. So how do we interpret this? There exists some n such that afterwards omega is in every single one. So omega is, maybe we just put it in simple language, omega such that omega is in, it's hard to paraphrase. It means if I go far enough in the sequence, I'm going to find an AK where omega is in there, and then omega is in all the ones after that. That's what this lim sup set is. And so we say this is the set of omega which occurs eventually. EV is eventually. Okay. Now let's just do a quick example to try to compute the the limit, if it exists, of a sequence of sets. So 1. So my sets are like this. This is AN. And so what I need to do if I want to get limit of this, it only exists if the lim sup and the lim inf exist and are the same thing. So let's start by computing the lim sup, which is intersection union n1 to infinity, k equals n to infinity ak. Let's just do one step at a time. So the union of all of these. So if I imagine the union of all these, it's like, so it begins at 1 over n, 1 minus 1 over n, union 1 over n plus 1, 1 minus 1 over n plus 1, and so on. And I see this lower bound is getting closer to 0, the upper bound is getting closer to 1, and so if I union all those, I'm going to get 0 up to 1, and so I just get 0 up to 1. The lim inf is what? Union intersection AK. So let's do this first. Okay, so intersection of these. So it's going to look like 1 over n, 1 minus 1 over n, intersection 1 over n plus 1, 1 minus 1 over n plus 1, intersection. And these sets are getting, like, these intervals are getting wider and wider. So the intersection is just going to give me the first one back. 1 over n, 1 minus 1 over n. And if I union those, just like I did before, I'm going to get 0, 1. So the limit of the sequence an as n goes to infinity, since the lim sup and lim inf both exist and are equal to the interval 0 to 1, I get the same thing. That's what the limit is defined to be. Okay.